Okay, today we're going to talk about something called series, and in the last video we talked about sequences, and so we just want to start off by talking about the difference between a sequence and a series. A sequence is really nothing more than a list of numbers that have a certain progression or a certain order to them. So in other words, this would not be a sequence. Let's say we had 3004, negative 28, and 7, and then 242. There's no order to that, and so this would not be a sequence. It would be just a simple list of numbers. So we're going to go ahead and erase that. But a sequence is an ordered list of numbers. So let's say 2, 4, 6, 8, 10. You can tell that there's an order to this. You can predict that the numbers are going to that come after this are just simply generated by adding 2 each time. And so that is a sequence. Now over here, the difference is a series is a sum. So I want you to think of, every time you see the word series, I want you to think of a sum. So it's 2 plus 4 plus 6 plus 8 plus 10. Series are separated with pluses, and sequences are separated with commas. And so that's basically the idea. This is nothing more than an ordered list, and a series is a sum. And we're going to see how to find the sum of a series in this video. Okay, now we have the formulas for generating the sum of a finite arithmetic sequence. Now let's break each one of those words down to make sure that the vocabulary does not confuse us or trip us up. Sum simply means that we are adding, so we're adding a certain number of terms together. All right, finite means we know how many terms there are. There are 3 terms, or maybe 5 terms, or maybe we're adding the first 10 terms, but it is a fixed number of terms, maybe 12 terms. It's just a certain number of terms, a finite number of terms. And then arithmetic, let's talk about what that means. Arithmetic, as we talked about with sequences, simply means that the numbers in the list are going up or down by the same amount each time. So you're adding the same amount each time, or you're subtracting the same amount, not to be confused with a geometric sequence or series, where to get the next term you must multiply by a certain ratio, a certain factor. So these two formulas here are for arithmetic series. So notice that both of the formulas you need to know n. So let's talk about what these letters are. N is the number of terms you are adding together. A1 is the first term in the list. And A sub n is the last term in the list. And so if you have these 3 things, you can use this formula here. Now, D is the difference, or it is what you're adding or subtracting to get the next term. So let's suppose you have the first term, and you have the number of terms you're adding together, but you do not have the value of the last term, but you do know that the terms are going up or down by a certain d. Then you would use this formula. But if you knew the number of terms, you knew the first term in the list and the last term in the list, then you would use this one. To me, this one looks like it's a little bit easier to use than that one. So let's see how this works on a specific problem. It says here, a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the preceding row. If the top row has 24 seats, how many seats are there in the entire section? So let's write down what we do know. We know the value of the first row. There are 8 seats in the first row. We also know that the last row, there are 24 seats in the last row. But notice, we do not know how many rows there are in this section. We do not know what n is. We do know what d is. It says that each row has 2 more seats than the row that came before it. So it's going up by 2 each time, so that is your d. Notice that both of these formulas require you to know the number of terms you're adding together. And so because we don't know that, we need to go back to 9.4, our study on sequences, and we need to use the formula that is called the explicit arithmetic formula. And that is a sub n is equal to a1 plus n minus 1 times d. All right, so this is the formula that we need to use to get the letter n. So let's just plug in what we know. A sub n is 24. That's the value of our final term, or the top row in this section. A1 is 8. That's the number of seats in the front row. We do not know n. That's what we're looking for, but we know d is 2. So we can now distribute. And so we get 24 is equal to 8 plus 2n minus 2. And so when we work this out, we're going to end up getting n is equal to 9. So that lets us know that there are 9 rows of seats that we are adding together. So now, because we know that, we can use this formula right here, and we can get the total number of seats in this section. So we're going to put a 9 for n, and then our A1 is 8 plus 24, the value of our final row, divided by 2. 24 plus 8 is 32, divided by 2 is 16 times 9. And that means there are 144 seats in this section. And that's how you use the sum of a finite arithmetic sequence. Okay, so now we're going to learn how to use the formula for the sum of a finite geometric sequence. So once again, let's remind ourselves a geometric sequence is a sequence of numbers whereby you have to multiply each term by a ratio, a number, we'll call that number r, in order to get the next term. So here is the formula right here. And notice that you need 3 things for this formula. You need to know the value of the first term, you need to know what you're multiplying by to get the next terms, and you need to know the number of terms that you are adding together. So let's see what information we have here. It says A1 is 4. That's our first term. And r is whatever you're multiplying by to get the next term. Well, notice our first term is 4. Our next term is negative 4/3. That must mean we had to have multiplied by a negative 1/3 to go from 4 to negative 4/3. And so we know A1, we know r. Notice, again, we do not know what n is. So now we know that the final term is 4 times negative 1/3 to the n, to the 10th power. Now, for this, we must once again go back to the formula for the explicit geometric sequence. And if you go back to your study on sequences, you will remember that a sub n for a geometric sequence is equal to a sub 1 times r to the n minus 1. All right, so I want you to just pay attention here that the exponent of our final term is 10. And this may be a little bit confusing. The exponent of our final term is 10. So what you want to do is you want to set the exponent here, n minus 1, equal to 10. All right, let's see if this makes sense. You have an r that's raised to an n minus 1 in the general formula, but our exponent in our problem of the final term is 10. So that means if you add 1 to both sides, that n must be 11. So there are 11 terms that we are adding together in this list. This is the first term, second, third, fourth, all the way to the 11th term, even though the 11th term has an exponent of 10. Now that we have that, we can plug it into our formula. So the sum of all of these 11 terms is going to be A1, which is 4, and then 1 minus. Now, once again, be very careful to put any value of r in parentheses when you raise it up to any exponent. And then you have 1 minus negative 1/3 here. And if you use a calculator, you will get this to come out to about 3.000, so on and so forth. So that would be the sum of all these numbers using the finite geometric sequence. In these next 2 examples, we're going to talk about something called an infinite series. And in the first 2 examples, we studied a finite series, which means we knew that we were adding up a certain number of terms. If you remember in the example with the seats in the stadium, there was 9 rows, so we were summing up 9 terms. In the second example, we were summing up 11 terms. But here, we want to sum up an infinite number of terms, meaning a million, gazillion, billion terms, and we want to see what the sum is approaching. And so now, obviously, in order for the sum of these numbers to converge, the numbers have to be getting smaller. And so we'll talk about that in a moment. But we want to talk first about what's called a partial sum. Partial sum is nothing more than summing up a certain number of terms in the list. So it says find the first 5 terms in the sequence of partial sums. So this is how we write this. P1 is the sum of the first term. Well, there's the first term right there. You're not really summing it up. It's just 0.1. So there it is. Now P2 is the sum of the first 2 terms. It's not the second term. It's the sum of the first 2. So that's going to end up being 0.11. And then P3 is the sum of this term, this term, this term. That's going to be 0.111. And then P4 is going to be 0.1111. And I think you can see the pattern. P5 is going to be 0.11111. Now we notice that this is a repeating decimal, 0.1 forever. And we may recognize that to be the fraction 1/9. So what we'll say is that this sum is going to converge. It's going to converge to 1/9. All right, so let's take a look at part B. And maybe part B we'll do down here. And it says we want to find the first 5 partial sums. So first partial sum is 10. The second partial sum is 10 plus 20, that's 30. The third partial sum is the sum of the first 3, that is going to be 60. The fourth partial sum is going to take 60 and add 40, that's going to be 100. And then the fifth partial sum is going to add 50 to that, because that's the next term here, that's going to be 150. Now, what do you notice the difference here between part B and part A? Part B, the sum is just getting bigger, so it's like a snowball that's rolling down the hill. The more terms you add, the bigger the sum is going to become, and so that's going to lead us to say that this sum is going to diverge. It's going to diverge, meaning it's going to head towards infinity. So anytime you have a sum that's heading towards infinity, it's called a diverging series. Part C. You have 1 and -1, 1 and -1. So you can see here that the terms are oscillating. So the first term, the sum of the first term is 1. But when you add up the first 2 terms, a 1 and -1, you get 0. And then when you add up a 1, a -1, and a 1, you get 1 again. And then when you add up the fourth term, you have a -1, so that's going to bring it back to 0. And then the fifth term, the fifth sum is going to be 1. And you can see that the sum is just oscillating back and forth between 1 and 0, 1 and 0 and 1. So this is an oscillating situation. So anytime you have a sum that's oscillating, that is going to be diverging, because it is not approaching a specific finite number. It just keeps going back and forth between 2 whole numbers. Okay, in this next example, we're going to talk about how to find the sum of an infinite geometric series. Once again, let's break those words down. Sum, we're adding up certain terms. Infinite means we're adding up an infinite number of terms, not 5, not 6, not 7, not 8, a million, gazillion, unending number of terms of a geometric series. And so essentially, this is the formula. It's a very easy formula to use. And this is actually, say, A1 right here. And essentially, you use this formula to find the sum of an infinite series. However, you can only use this formula if the series converges. Let's talk about that. All right. A geometric series converges if the r, the number you're multiplying by, is less than 1. Let's see if that makes logical sense to you. Let's just say we have a list, and let's say the list is 8 plus 4 plus 2 plus 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. I'm going to keep going, plus 1/32 plus 1 over 64, plus 1 over 128, plus 1 over 256, so on and so forth. What you'll notice is that the bigger the denominator gets, the smaller the overall number gets. And so if you're adding a really small number to a bigger sum that's already been developed over 8 plus 4 and 2 and 1, those are bigger numbers, you're not really changing the overall sum a lot. I would encourage you to plug these into the calculator one by one and just see that the sum is not changing much once you get out here, because these numbers are so small, they're close to zero, that they're not really contributing a lot of value to the overall sum. And so the only way to get this type of situation is if you're multiplying by something less than 1. Notice you're multiplying by a half. So the numbers are getting smaller and smaller until eventually the numbers are going to be negligible. So that is the only time that you can use this formula that we have before us, as if it is a converging geometric series. So if it is, we're going to use this formula. So let's look at part A. You have 3 times 0.75 k to the k minus 1. So we first need to find A1. Now you have to be careful here because you have to pay very close attention to this index number. A lot of students will think that A1 is simply this number here. It is not always the case. You must plug this index into the formula to figure out what is the value of the first term. So let's plug in k equals 1. 1 minus 1 is 0. Anything to the 0 power is 1. Times 3 is 3. So we know our A1 is 3. Our R is 0.75. That is less than 1. So that means the numbers in the list are getting smaller. So if that's the case, we can use this formula. We know it converges. So we're going to put 3 over 1 minus R. And R is 0.75. So we could either use a decimal or a fraction. And so 3 over 1 minus 0.75 is 3 over 0.25, which I'm going to write as 1/4. You can flip this fraction and multiply it times the top, and you will get approximately 12. I put approximately because it will never actually equal 12, but it will get closer and closer to 12. All right, now that you've seen it done once, maybe you can pause this video and see if you can do part B. All right, let's figure out whether it converges or diverges. You can see that the R is -4/5. That is less than 1, the absolute value of that. So yes, it converges. The question is, what does it converge to? So we're going to plug in our 0. We get 4/5 to 0, that is 1. So our A1 is 1, and our R is -4/5. So we're going to use our formula, 1 over 1 minus -4/5. So that's going to be 1 over 9/5. And then we're going to flip and multiply, and we get 5/9. And that is what this converges to. All right, part C, you have pi over 2 to the n. And this is a tricky one because if you're not careful, you would just go straight to using this formula without checking to see whether it converges or not. And this actually does not converge. Pi is 3.14. Divided by 2, it gives you approximately 1.57. That is greater than 1, and therefore it does not converge, it diverges. If it diverges, you do not need to find what it diverges to, because it's going to diverge to infinity. So it's kind of redundant. So you just say it diverges. All right. And then part D, you have 1 and then 1/2 and then 1/4 and then 1/8. So you can see that the A1 is 1 and the R is 1/2 because that's what you're multiplying by to get the next number. So we know it's going to converge. So we plug it into our formula. We have 1, which is A1 over 1 minus 1/2. And that's going to give us 1 over 1/2, which is going to converge to 2. So you'll say it's going to converge, just converges to 2. And that's what you'll say. That's how you use the sum of an infinite geometric series. And by the way, this formula is the only formula that you will need to use for any problem that says infinite. So as soon as you see infinite in the problem, you know that this is the formula for that problem. In this final example, we want to figure out how to come up with a fraction that will give us a repeating decimal. So we notice that the decimal is 0.234, repeating forever. This is a very, 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 very easy problem. What you want to do is you want to take whatever numbers are repeating and take off the decimal. So you'll write this as 234, and then you'll divide it by however many digits you have. 234, that's 3 digits. You're going to divide that by 999. And you can try this for yourself. If you plug this into the calculator, you will get this exact repeating decimal. So let's say we were looking to do 0.64646464 repeating. Well, you would say, oh, the 64 is repeating, so I'm going to take 64 and I'm going to divide it by 99. There are 2 digits in 64. We need 2 nines there. And we'll do one more example. Let's say you have 3.27272727. What you want to do in this example is you want to take the 3 off, and you want to say 3 plus 27 over 99. And then you can use this 3 over 1, and you can get a common denominator. So I'm going to multiply by 99, and that looks like it's going to be 297, and then we'll have plus 27 over a common denominator of 99. Hopefully I'm doing my math correct. And then you'll add 27 to that, so that'll be 307, that'll be 317, so that'll be 324 divided by 99. If you plug this number in your calculator as a fraction, you should get this repeating decimal. And that's a simple process for taking a repeating decimal and coming up with a fraction that expresses that repeating decimal.